Okay, so in this sense, we now consider our reduced partial differential equation where we have our main nonlinearity, and that is that the relativity, and we know relativity, we can also write 1 over permeability, depends on the magnetic field itself. We assume an isotropic material, so in all directions we have the same property for the magnetic permeability or relativity. Very important is to be noticed is, as you can see here, that this pH curve, as we call it, so we have here on this axis the magnetic field intensity, the amplitude, and here the amplitude of the magnetic flux density. And we have here this nonlinear curve, which is monotone increasing. So it is strictly monotone increasing, which is a very important property clearly when we will then go towards a Newton method. Okay. On the other hand, if we are just going back, we clearly have now written it as relativity. So looking at the relativity, where we know the relativity is nothing else as we have H over B. It is not monotonic increasing or decreasing. So you see we start here with a larger value, we come to a minimum, and then it is increasing and increasing. And that is due to the fact, if we go back, that for the ferromagnetic materials, you mainly have here, if we zoom in, then you have here such a behavior that you first have a slope which is smaller and then it is increasing. Yeah? So if we here have again in this way here H and here B. And therefore we also have here somewhere a turning point, and that makes it clearly not as easy for numerical computations in order to converge with your Newton method or fixed point method. Okay, so the dots, what you see here are nothing else as measured values we obtained by measurements, and clearly the question arises how to approximate now here these measurement points, or should we do a interpolation which we need within our scheme, because we have to evaluate then for different computed magnetic fields in all our finite elements at different values. So we should have an analytic function by hand at the end. So important is, as I already told you, that this pH curve is a monotone. It's strictly monotone. So perhaps we should also write it here. So it is strictly monotone according to physics. We know the computation is as follows, that our relativity we have here is nothing else as we take the values we have measured for the magnetic field intensity and divide it by the according values of the magnetic flux density. Now, you also note that within a Newton method, we will also need the derivative. So this nu prime just means it is the derivative of our function nu with respect to b. So we explicitly can write it down, as you know, since we have this function. If we do this derivative, then it is just in the denominator we have b squared, and then we have here the derivative of h with respect to nu multiplied by b minus h as a function of b. Now, the question clearly arises, what is better, to an approximation or interpolation? We should always have in mind that in practice, when you measure any physical quantity, we also do measurement errors. So that's the first important point. And the second important point is that we want to have this new curve or this pH curve approximated in a smooth way. We do not want to have oscillations. So that would be the kill, let's say, for a Newton method. So that means it would be nice to use a approximation and do this approximation by so-called smooth splines and apply a optimization process. And as we see here, important always for optimization is what is your functional. And as you can see here, this is a functional which has two terms. And the first term here is the following, that we have the second derivative of h with respect to b. And if you have a function and you take the second derivative, then you get the curvature. And the second term here is the difference between measured values of h and what we obtain with our function, then analytic function, for which we have to compute the coefficients. So that means in a first case, you see we have this important parameter here, alpha. And now if alpha is small, then the second term here will not be very important for our function. That would mean we try to optimize our coefficients of our splines in such a sense that we get out a very smooth function. Yeah? But perhaps then this spline function will be too far away from our measurement points. On the other hand, what we can have, if you take alpha very large, then clearly the second term will be the most important term. And you try to do approximation in order that you really try to meet the measurement points, and that can result in a spline function which is quite oscillating. Yeah, so a very practical approach is to use the so-called discrepancy principle, which means that we start with the alpha. In this sense, let's say where it is really large, and which means that we try to meet somehow the measured values of h and b with our spline function. But then we start to decrease this alpha value in such a sense, as you can see here, for example, by the factor 2 with the power of minus j, that you look at the L2 norm between measured values and the values you get out of your spline function, and you decrease this alpha, which means you wait more to get a smooth function and less the accuracy between your evaluation of the spline function and the measured values, but you should somehow keep the measurement error. So if you have an idea about your measurement error, then let's decrease this alpha in such a way that at the end it is small, but it should not be made smaller in such a sense that the spline function you have obtained and take the difference to the measurement values then is larger than the measurement values. And this is a very powerful tool to have a so-called regularized least square functional, where this alpha is here a kind of a regularization parameter. So you do a lot of sequences within your optimization with a fixed alpha, but from one optimization to the next, you decreases in order to get a smooth function, which is good for our numerics. Then when we solve with a Newton method, or also the fixed point method, our nonlinear partial differential equation, but it should not be in this case that the error we have between the measurement values and the evaluate values according to the spline function being larger than the measurement error. So this is the criterion you should use in practice. Okay, so our goal is now to get a Newton scheme. And as you know, the finite element methods are such that this numerical scheme is not directly approximating the partial differential equation. We first go over to the weak form, and then we approximate the weak form with the ansatz according to the basis functions. And therefore, we will see that we will also transform this idea towards the Newton scheme. So a standard Newton scheme is nothing else as written here. You try to approximate your nonlinear operator, which is our partial differential equation, by evaluating it at a specific point plus the derivative of our nonlinear operator, and you call this the so-called Frechet derivative, at the already known value of the vector potential. So this is iteration k, and we want to set up now our scheme for to get the value ak plus 1 in the direction of s. So s is our gradient in this sense, so the increase how we should update our current solution ak. And this is clearly approximate 0. You would have to take into account also higher order terms, so the second derivative, third derivative, and so on. But we stop at the first derivative, which is the standard for a Newton method, and set this to 0. So if we set this to 0, then we clearly come up to this approach here, that on the left-hand side, you have here this Frechet derivative in the search direction. This Frechet derivative actually is like your Jacobian matrix, and this is equal to minus, since we have set this equation to 0, to evaluate our nonlinear operator at ak, where we assume that we already know ak. Yeah, and then the new value we just get by adding to ak our search direction we have for each unknown within our computational domain. So A as well as S are collecting all our unknowns, and you know the unknowns now for us in electromagnetics, since we will use edge finite elements are along the edges. However, in order to get a stable method, we should include here a so-called line search parameter. So we know in which direction we should go, that we get out with S, but how large we should go for this step is still an open question. Should we go the full step, which means eta equal 1, or we should reduce this step? This is an open question, but a very important part in order to get a stable and converged solution at the end. So this is currently open, how we should choose this, and we will discuss about it. Okay, so the good news for us is that this Frechet derivative in the direction of S can be computed by this simple approximation, and it is again a approximation we have up to second order. So we just evaluate, as shown here, our nonlinear operator at AK plus S minus evaluating the nonlinear operator at AK. Yeah, and the nonlinear operator clearly would be our partial differential equation, but we will not use the partial differential equation. For this operator, we will use the weak form. Yeah, and that is then very appropriate for us, and that will give us a general approach for each partial differential equation you want to solve with a finite element method. You will exactly use these steps and end up in a Newton method and simplifying it in a fixed point method, as we will see quite soon. Okay, for this we have to do some steps, but as you can see here, we have our weak form, which is written here. Now, if we take what we have on the right hand side and put it to the left hand side, then this equation is equal to 0, and that should be or will be our nonlinear operator now, for which we want to compute the Frechet derivative in the direction of the increment S, because we want to solve for this increment S. If we have the solution for the increment S, as we see here, then we can compute our new vector potential along all the edges AK plus 1. Okay, so how to compute it? We know we have to evaluate it now at AK plus S and subtract this operator by evaluating it at AK. So let's have a look at the first term. So we have to evaluate our material parameter, the reluctivity, at the new solution we don't know. The new solution will be AK plus S. We have to take the curl and then the absolute value, because this gives us actually the new flux density that would be BK plus 1. Then we have to put in, as shown here, the curl again of AK plus S, and then we have the dot product with the curl of the test function. And from this term, clearly we also have to consider this term, but this term will be always the same if you evaluate it at AK or AK plus 1, therefore it will cancel out. And so we just have to subtract here now the evaluation of our weak formulation at AK. That's why we have here the curl of AK, which means this here is BK. Yeah, and then we have the curl of AK dot product with the curl of the test function. Now, we have to do some steps, and there are clearly some tricks in order to come up to the final formulation we can evaluate, because what is not possible at this step is to evaluate here our nonlinear function, the reluctivity, as a function of the absolute value of B, because we don't know S. We cannot evaluate this. So the first idea is the following. We try to add and subtract this term. Why do we want to do this? Because then we have the possibility that we get here the evaluation of the reluctivity as a difference between BK plus 1 and BK. Yeah? So what we get out is now here this extended term, which at the first glance will also not help us, but we know this is something always we can develop in the Taylor series, and then just consider up to first order. And we have then in addition here the curl of AK plus 1 dot product with the curl of the test function, and we have this additional term. So we have no problem with this term. We know that the curl operator is a linear operator. We can rewrite this as the curl of AK, which we already know, and the curl of the increment S we want to compute. This is totally okay, because we can evaluate our nonlinear function, our nonlinear relativity for BK, which is the curl of AK. And then we have just the curl of S for which we want to solve for this S. So we have to concentrate now on this function. And clearly what we will do is we will have here to evaluate this function here at AK plus 1, which means we will develop it in a Taylor series at the developing point AK. And that is done on this slide here, as we have the following. Well, when you evaluate this function here in a Taylor series, you first evaluate it at AK, and since you have then your relativity to be evaluated at the absolute value of BK, and here the same, that will cancel out. In the Taylor series, you get then the first order term, which means you have to take the derivative of our relativity function depending on the magnetic flux density. And you have to evaluate it at AK, or let's better say the absolute value of the curl of AK, which we know is here BK, which we can do. And in addition, we have this term here, which is a nasty term still, because that is the increment, what we have evaluated, the increment of the curl of AK plus S, absolute value, minus the curl of AK. Okay, but for this term, which is rewritten here, we remember what we have learned in school, that a square minus b square can be written as a plus b multiplied by a minus b. Okay, what we have here on the left-hand side is exactly this one. Yeah, so this is this part, which means this term here can be substituted by a squared minus b squared over a plus b. Now let's look at the denominator. So we have here a plus b. A is the absolute value of the curl of AK plus S, and b let's be the absolute value of the curl of AK. Yeah, and in the denominator, we then have the following. We have to evaluate a squared minus b squared. So we have the absolute value of the curl of AK plus S squared minus the absolute value of bk squared, which is the curl of AK absolute value squared. Okay, so from this, we can rewrite the terms as shown here. So if you take the absolute value of the curl of AK plus S, yeah, you know, we can rewrite here this argument by the curl of AK plus the curl of S, yeah, because the curl is a linear operator. And this is here to be taken as an absolute value and then squared, which means what we have actually is the first term. So it's the absolute value of the curl of AK squared. We have the absolute value of the second term squared, and then we have the mixing, which is 2 times, as we know, the curl of AK dot product with the curl of S. And the second term is minus the curl of AK squared. So we see already that this term cancels out with this term. Yeah, and now since we always do an approximation up to order 1, we can further simplify it. That is why here is not equal, it is approximate, which means that we can cancel out this term. It is of second order because it's the curl of the increment, and that is squared. Yeah, and if you look at the denominator, then clearly more or less we can cancel out here this s, and this would give us 2 times the absolute value of AK. Yeah, and these two and these two can be cancelled out, and we end up in this quite nice term, which is now a term we really can compute, or where we really have in a very nice form the curl of our increment we want to compute. Okay, that means we have now done the approximation of this term. So if we go back, we were already here, and the only problem we have here was this term. Yeah. And now for this term, we have seen we can substitute it in an approximation up to first order by this term here. Now, let's plug it in. And if you plug it in, we can now have this expression of the Frechet derivative in the increment s, which we want to compute, this increment s, for all our unknowns along all the edges. And this is this quite long term here. Yeah? But everything in this case is okay. As you can see, we have to evaluate mu prime at the absolute value of pk, which is not a problem, which we are able to compute because we know already our solution at the iteration k. So we can also compute the curl of AK, we can compute the absolute value of the curl of AK, and this term here we can rewrite as the curl of AK plus the curl of S. Okay, and then we just have here the curl of the test function. But what we should not forget is that we have within this long term here the curl of S, and we have here the curl of S. So this is again a second order term which we can neglect because we just need to take into account all terms up to first order. So therefore we can also reduce this complex term by neglecting the terms where the curl of S with the curl of S is computed within a dot product. Okay, so what is just written here, I've already also written on the slides so that we use the property that the curl is a linear operator, and we end up now in this formulation, which is fine for us because if you look at this quite long term, we just once have the curl of S. We can evaluate our new prime. We can compute this term here because we know AK. We can compute this term here, compute this term. This is the curl of the test function. And so just what is left here is the curl of the increment. So this is now a term where we can plug in our approximation with the vectorial basis function, and clearly looking at this term here, we can also do this and plug in here our ansatz functions. Okay, so that means all over we can come up to the following quite long form, as you can see here. Now we also have put here our source term in. You know, I just go back to remind you on where it is here. On the right hand side, we have minus our nonlinear operator, which is our partial differential equation in the weak form to be evaluated at AK. What we have computed was this term here with all the steps and tricks I just have showed you. Okay, so that means what I just have substituted here is something like this. That's the unit vector in the direction of BK, which means it's the curl of AK, which is BK, over the absolute value of the curl of AK. Yeah, these are such terms you can see here, for example, this term here. Yeah. Okay. And I have put everything to the right hand side, what we already know. So what is left are these two terms. So you see once we have here a term is included the curl of S we want to compute with our relativity depending on BK. And once a term which is a little bit more complicated and where we have included here the derivative of our nonlinear relativity function with respect to the magnetic flux density B. Okay, so we get now our finite element formulation as follows. When we substitute now our ansatz within this weak formulation, with our vectorial basis function, we get out at the end a stiffness matrix, which is a standard stiffness matrix, but depending on AK, as you can see here. So this term, what we have here, excluding then clearly the S here, but out of this term, we come up to our standard stiffness matrix, and this quite long term will give us this so-called tangential stiffness matrix. You can also call it the Jacobian. And you see in both terms we have the S, for which we want to compute our increment, with which we update the solution we have obtained from the previous iterative step to get the new solution at the iterative step k plus 1 for the magnetic vector potential. And again, I have included here our line search parameter, sometimes also called the relaxation parameter. What is the nice thing is the following, that when you neglect k tangent, you just end in the standard fixed point method. Yeah. And as you know, for the fixed point method, we don't need to evaluate our nonlinear function, which is our relativity, the derivative of this nonlinear function. We just need the nonlinear function to be evaluated directly. Okay, so let's have a graphical illustration of a fixed point method and of the Newton method. Let's start with the fixed point method. Okay, so to understand it, on this axis here, on this axis, we have the axis for our solution. Yeah? And the solution is the vector potential along all the edges. And what we put here is our system matrix, which is depending on the solution itself multiplied by A. And what we have here is a line. It's not shown here. I just look if I have made the abbreviation. No. So this is this F. Yeah, I have not written it here, but this is this F. I just go back. So this is this F we have here. And it's clear if we meet with this term F, we are at the solution point as shown here, this would be the solution point. Yeah? So that would be then the correct solution. Let's call it A star or whatever. Yeah? And as you know, for the fixed point method, we always go along the second, and then when we meet our right hand side, we have our first solution. Yeah? Then we again go from the 0 point here through what we have obtained, and we obtain, as you can see here, the second solution. And as you can see here, looking here, we can make nice progress, but if the slope here is small, we need a lot of iteration until we come up to our solution. So a fixed point method perhaps is more stable to come up to a solution, but it could take you a lot of steps, iterative steps, until you come up to the solution. On the other hand, the Newton method, we know we go along the tangential direction. That is why we have to compute this Fréchet derivative. And as you now can see here, we go, as you can see here, along the tangential direction and get our first solution. And in this point, we now again, due to setting up the tangential stiffness matrix, along the tangent of this nonlinear curve. And we come up to the second solution, iterative solution. And you see perhaps already from here to here, perhaps you already get the final solution. So you see, for this case, I have drawn here, the Newton method would be extremely efficient. We would just need about 3 iterative steps compared to the fixed point method, as you can see here. Okay, now what clearly has to be discussed before we go on and say, okay, when should we stop? You will never get the exact solution. So we need a measure to evaluate our current iterative solution if it is already very near to the solution. So we need the so-called stopping criterion. But before we discuss the stopping criterion, we discuss the line search parameter. And this is, or the optimal relaxation parameter, which we have called eta. Okay, so again, this is more or less an optimization problem. And so we have to set up what is our optimization functional. We want to minimize. There are a lot of possibilities, but there are also a lot of approaches where in order to get this optimal relaxation parameters, you again have to solve a lot of forward problems, meaning you again have to set up your system matrix and solve it, which is then very time consuming. Now, a nice approach is to take as a characteristic functional this one here. What is this one here? You have computed your first increment within your iterative process and want to get now the step length parameter eta to multiply it with s. So we could project this increment we just have computed on the residual. R is the residual. And what is the residual? Well, it is, as we know, nothing else as the right hand side in our discrete form. And you see it, this is the right hand side. Yeah? But we should evaluate now the stiffness matrix already at the new vector potentials AK plus 1, and also here substitute AK by AK plus 1, because if this gets to 0, well, then we should be at the solution. Okay, so as you can see here, this is shown here. We have to set up again our stiffness matrix and multiply it with the solution. And now within this formulation, we have this nonlinear, not nonlinear, this relaxation parameter, for which we want to get the optimal one. So we have to set up again, which is time consuming, clearly, our system matrix, but we don't have to solve the algebraic system of equation. And a simple approach is to say, okay, I have a quadratic function for g that is an offset plus a linear term plus a quadratic term. And so we have more or less 3 coefficients. Well, we don't have to evaluate here and do anything new when we evaluate this for eta equals 0, because then we should get A0. That is the solution we have obtained in the previous step. Then you have to evaluate it, let's say, in the center between eta 0 and eta 1, which is dot point 5. So here we have to set up the system matrix and multiply it with it and subtract it from our source term. And once we do it for eta equal 1, where we do a full step. Yeah, so in this sense, then we have 3 evaluations of G and can get the 3 coefficients. And from this simple scalar function, it should then be no problem to get it where it takes on the minimum value. And for this minimum value, we can evaluate then the correct relaxation parameter or line search parameter eta. Okay, so this is the approach. And if you look to literatures for all nonlinear partial differential equation, not only in electromagnetics, also structural mechanics or acoustics or whatever you are solving, you will have here very similar approaches. Okay, now the question clearly which arises here is, when should we stop? We do a numerical computation, you will never get the exact solution, but we can stop when we are very nearby. So a simple criterion would be, you just look at the difference you have obtained at iteration k plus 1 and iteration k. And if this is smaller than some value, let's say 10 to the power of 6, then you stop and you assume to have a very accurate solution of your problem. What is here is the standard L2 norm, which means for all unknown, we take the difference, square it, sum them up, and at the end, take the square root. The question is, what is a correct value for this epsilon? And it's called here epsilon abs for absolutely. Once you will have a computation where you will have very large values of the magnetic vector potential, once you will have small values, it's depend where you compute the electromagnetic field, how large your excitation, so the electric currents, for example, are, or if you do a computation for a transformer or in a MEMS system. So the better way is to use a relative value, which means you divide this absolute norm we have here by the L2 norm of AK plus 1. Yeah, so that would mean you take this term here and put it here in the denominator. And then it's easy in this sense. So if we take here as shown, for example, a value which is about 10 to the power of 3, then that would mean it is 0.1%. And please consider this is not the relative difference in each of your unknowns, so the vector potentials along the edges you are computing. It is you sum them up and at the end you take the square root. So 10 to the power of 3 is already quite strictly, but if you have enough time to wait for the solution, it is a value which you should really use. Okay, so in this sense, for using the error criterion, you should use, as shown here, the relative norm and choose as a stopping value for this epsilon, something like 10 to the power of 3. Now, what I have on this slide is the second criterion. And the second criterion is the residual criterion. And that also clearly makes sense because here you actually, as you can see, you measure how large you are still out of balance between the left-hand side of your algebraic system of equation and the right-hand side. And here again, it makes sense to go to a relative norm. And for the relative norm, it makes sense to normalize it to the L2 norm of your right-hand side, which is F. And here again, it would be good if you can reach here a value which is 10 to the power of 3. Then you can be sure that you have a quite accurate solution. Now, why I always advise to use both criteria, the error criterion and the residual criterion, I want to demonstrate again graphically. Okay, let's have here the following. We have here again on this axis, it is the residual, so left-hand side of your algebraic equation minus right-hand side. Here is the solution, and let's say we have such a nonlinear behavior, then as you can clearly see here, if you use the error criterion, we are already very near with this iterative solution at ak plus 1 at the true solution. But when you look at the residual error, you are still far away. So that's perhaps a problem. You think you are at the solution, but you are not really there at the correct solution. Please also consider, and that is also important, we compute ak plus 1 by ak plus our relaxation parameter s. So clearly, if your relaxation parameter is chosen then by your optimization very small, well, then it's clear that ak plus 1 and ak will be very similar, and then the error criterion will give you a value for the L2 norm, which is very small. So this also should be kept in mind. On the other hand, it can also happen, this problem, when you apply the residual criterion for this strange nonlinear curve I show here. It is going like this, and then you have a very small slope somewhere here. You would have the exact solution, and you go up here. When you put up the graph again, the residual left-hand side minus right-hand side in the L2 norm, and here the vector potential. Then here we would have at this iterative solution at the iteration k plus 1, a small residual, but we are still far away from the true solution, which will be, let's say, somewhere here. Okay, and since we don't know how actually this curve between the residual and our solution looks like, because we have an n-dimensional system, because we have n unknowns of the vector potential along all the edges of our computational grid, that is not easy to be evaluated. It therefore makes sense to use both criteria, the residual criterion and the error criterion. Okay, now I want to demonstrate by this simple setup, it's just a 2D example of an iron core, how important actually it is to do within electromagnetics, where we have ferromagnetic materials, to really do a nonlinear computation. And more or less, linear computation will not result in physical fields. Okay, so we do on a cross section the computation, which means when we cut through, we will have here a part of the coil, and we will have here a part of the coil. Let's say here, for example, the current goes in, and here the current is going out. You could also set up a three-dimensional example, but I want to illustrate it, how important actually it is to include the correct material nonlinearity in an electromagnetic computation. So you see here, it is a very coarse grid. When you look here at this picture, and for each finite element, I just have plotted here the magnetic flux density. Well, and what we get out is we clearly have these so-called hot spots here at the corners, where we have here the highest value of the flux density. And if you look then at the other parts, well, we have almost no homogeneous magnetic field. On the other hand, from measurements, we know that clearly in these regions we will have a low magnetic flux density, but at least here we should not have along such a line such differences, and we should not have these hot spots actually here. And if you refine your grid, then you will get your hot spots, which will be perhaps not 2.4, it will be, let's say, 5 Tesla or even more. On the other hand, we know in ferromagnetic materials like iron or steel sheets, we somehow are in full saturation at 2.5, 2.6 Tesla. And that is what you now see here. For the nonlinear computation, yeah, we have highest value, which is about 1.5 Tesla, which is reasonable. And now you see, you clearly still have here some discrepancy. It's not exactly at the corner the same value, but that you will also have in reality if you do measurements. But in this region, this region, this region, this region, we quite have a homogeneous magnetic field, as we know then also from measurements. And this is clearly a question of your excitation, how large the current is within the coils. Anyway, for most of our devices, it will be a must, let's say, to take the magnetic nonlinearity, this material nonlinearity, into account. Okay, so this was now the overview about computational electromagnetics, which I would say is the real complex part within electromagnetic mechanical coupled computations, because most of our devices we are interested in, if you look at the transformer, at the electrical drive, at the magnetic valve, whatever, we can very often apply their linear elasticity for the mechanical part. So it is a linear partial differential equation. But for the electromagnetic field, you have to take into account this nonlinearity, the material nonlinearity within the electromagnetic field in ferromagnetic materials. But we also have a very heavy challenge now in the coupled system, because as you know, when we have such ferromagnetic structures in a magnetic field, then we will have electromagnetic forces, and these electromagnetic forces will deform or move, or in the machine rotate the mechanical structure. Yeah, and now the question is how to take this into account, that actually a rotor is rotating. Yeah, or you have a structure like a copper plate in a magnetic field, and due to the Lorentz forces, it is strongly deformed. Well, what tells us physics when we derive the equations, and what actually effects we have there and we have to take into account? Okay, for this sense, I have now again the full partial differential equation, including our motional EMF, electromagnetic force term, which is here that we have, when we know the velocity of the deformed structure or of a moving structure cross product with the magnetic field, when you have a structure where you have electric conductivity different from zero. Now this is nice what we derive, but the question is, what is the case? And that I try to show you for this simple ferromagnetic body as a lift magnet. And let's say we have a special ferromagnetic material where here the electric conductivity is even zero. Yeah? Okay, but then we all know that the most important regions are the air gaps here. And the smaller the air gap at constant current in the coils, the larger the magnetic field will be within this setup here. And so if you lift here this part, this ferromagnetic part with conductivity zero, the air gap gets smaller, so the magnetic field should increase. Which means, where do we have this in this partial differential equation? Even this term is not of interest because the conductivity everywhere is zero. Well, it is clear that somehow we always solve this partial differential equation on a given geometry. But now, as we see, the geometry is changing because the air gap is getting smaller and smaller due to the electromotive force on this term here. We also have an electromotive force here on this structure, but we assume that this is somehow mechanically fixed and this can move. Okay, and that you can simply also compute by a magnetic circuit, and what you will get out is just shown on this equation here. And there we have this distance x. This is the distance x0 we have without any current, let's say, within the coil. And then if you switch on the current and increase it, then this running coordinate x will increase, and the difference gets smaller, meaning the air gap gets smaller. And then clearly by this simple computation using a magnetic network, the magnetic flux will increase and increase when the air gap gets smaller and smaller. Okay, but that means in this sense, we have to compute our partial differential equation always on the actual geometry. And this is a big challenge, which I want to show you here. Now, what does this actually mean to solve a partial differential equation on a deformed geometry? So let's look at a point in space P, which is at position X at time T, as shown here, and due to the mechanical forces, this point, this material point, will come up here and we'll have the position X plus delta X. So we have to change delta X. So we will have in 3D to add here in X direction delta X, in Y direction delta Y, and Z direction delta Z. And that will be the position at time T plus delta T. Okay, so we have to look at the change of the magnetic vector potential, which we can simply write here as delta A over delta T. And we know that we have to evaluate then our vector potential at X plus delta X and T plus delta T minus A at the old position and previous time over delta T. Now, for this function here, we should do a Taylor expansion. And please note, we have to do a Taylor expansion with respect to the coordinates and time. You can also say, I have 4 coordinates where the 4th coordinate is the time. Or you say, I have 3 space coordinate and 1 time coordinate. Okay, and that is written here, our Taylor expansion. Well, that means we first have to evaluate the vector potential at X and T. And then we have the first order derivatives, we have mixed derivatives, we have second order derivatives, further higher order mixed derivatives between space and time, and so on. So here is the first order derivative of the vector potential with respect to time increment delta t. What we have here, it is the first order derivative with respect to the x coordinate, and the x coordinate changes with respect to time. And the same for the y coordinate and for the z coordinate. And then clearly we can rewrite this, since we have the derivatives of the coordinates with respect to times. This is exactly the velocity, how with which velocity the coordinate changes, which means we can also rewrite this in a very compact way by taking the dot product between the nabla operator and the velocity, and this new operator is operating then on A. Yeah, and don't forget always our delta t here. Not forget, clearly. Okay, so if we let, and this is, as written here, approximation, because we neglect all higher order terms. Let go delta t to 0. Then we have the total change. We come up to the total change of the vector potential with respect to time, which is our local change with respect to time, and this additional term, which we call also the convective derivative. Okay, now let's look at this term. How this term, what we have obtained, yeah, what we actually do. When we always compute on the actual deformed geometry, then we have the total derivative of the vector potential. And that means not only the partial derivative with respect to time, as shown here, but also this additional term. Now the question is, this additional term, does this correctly include our motional EMF term? Let's have a look if this is correct. If we look here, then if you apply a vector identity, we get this very nice relation here that the conductivity velocity cross product with the curl of A gives us the gradient of the dot product of the velocity with the vector potential, but this number operator is just operating on A, not on V. Otherwise, that would make no sense. Minus this term here. And this is exactly what we also have just seen before, this convective term. So if I go back, we have this convective term included, but please be careful, we don't have this term included. So that means by doing this computation always on the deformed geometry, the motional EMF term is not correctly modeled. So that means for us that the correct PDE for moving deforming bodies, which you always solve on the deformed geometry, is not only this term here. What is missing is this term here. So in order to correctly model this motional EMF term, when we solve the partial differential equation analytically or numerical, however, we have to solve now this partial differential equation where it is not allowed to neglect this term. I'm quite sure that all commercial tools neglect this term. So be very careful. That term could have an impact in your computation. The good news, and this is always that we have good news, is in 2D. In 2D, in the plane or axisymmetric case, yeah, this term is always zero. Why is this term always zero? Who has an explanation? You see what we take here, I'll just write it here again, the dot product between the velocity, how the body is moving or deforming, dot product clearly, with the vector potential. Now, let's assume the 2D plane case. Then we know if we do a computation in the XY plane, we have discussed that this vector potential is just one component depending on X and Y in Z direction. Now, why is the dot product with the velocity zero?
Yeah, because if there is a movement in Z direction, then it wouldn't be the plane case.
Yes, exactly. You could have, as we all also have discussed, the movement also in the Z direction, but when you want to do a 2D computation, it is always, okay, it could be exact, but exact always just for theoretical problems. For a practical problem, we always have a structure with a finite dimension in the third direction. Yeah, and then exactly correct as you just explained. We assume that we have no velocity in the third direction, so in Z direction. So again, you see in 2D, everything is simpler, and sometimes even in the analytic case, it is just fulfilled. Everything, as we can see here, for the vector potential, we have an automatic gauging of the vector potential, for example, and so on. Okay, the important news for us is, in order to have a physical correct formulation, we have to compute our magnetic fields always on the deformed geometry, which is just written here, and this is also called within the within computational mechanics as the updated Lagrangian formulation. Yeah, you always update your coordinates in such a sense that you do the computation on the deformed geometry. If we do this, we have one problem. We don't model the motional EMF term correctly, which means we have to correct our partial differential equation, which is now here, to add on the right hand side, which is then clearly also an unknown term. We have to add this additional term to have a physical correct description also within the PDE of the motional EMF term. Okay, so we know now what is our partial differential equation, the correct partial differential equation, which we have to solve when we have deforming moving bodies, and which we have to solve always on the deformed geometry. Now, in a discrete setting, this makes a lot of problems, because it's clear that when we have solved for the mechanical part, we get the mechanical displacement, and that we have to add then to the coordinates of our computational domain. So in each finite element node we have within our whole computational domain, we just have to add the deformations. Now, in our case, we just assume that we have deformations here of this body. Yeah, let's assume you don't have any deformation. Perhaps let's also say it is like a solid body movement, because the deformations really will be small. We just have here a movement in this direction of the lifting part here. Yeah, but then you have a problem, because what we get out is, in these nodes along the yellow line, we get new mechanical deformations, and that we add to the coordinates. But when we add it to these coordinates along the line, after some time, then the coordinate here will have a larger value, let's say y value, so this is x and y, as the coordinate here of this finite element. So it would mean this coordinate would be larger than the coordinate of this finite element of this node. That's not possible. In practice, you would get a negative Jacobian when you compute the entries of your system matrix. Okay, so the computer program, simulation program, will break down. One approach is to somehow not do a remeshing of the computational domain, is the smoothing mesh technique. Yeah. Actually, you see, the problems we get is because the electromagnetic field is not only in the solid parts, it's also in the surrounding air. Yeah, I already have cut here. Perhaps we also have to take here some additional finite elements to correctly describe some stray field we have here also on this side. But when you do computational mechanics, we don't have to compute it in these air regions here. You just would compute it in this structure and perhaps in this structure. So no problem for computational mechanics, but a big problem for computational electromagnetics. So what does this mean, this smoothing mesh technique? So the idea here is simply the following. The simplest idea, and this is, I write here one, would be to also extend the computational domain, for the mechanical field into the surrounding air. Clearly, in order to have a correct mechanical computation, we would apply within these regions here a very soft material. Yeah, so the stiffness of this material would be very, very small compared to the stiffness, let's say, of this material here. But you will always have some reaction back, and it is not fully physical correct. Because if you would include this part also here, and along this dotted line here, black line, set here homogeneous mechanical directly boundary conditions. So you fix there the degrees of freedom for the mechanical displacement. Then you would get also a deformation within here this gray region. However, yeah, you will get deformed elements, but perhaps you will heavily get distorted elements. And therefore, this second idea, which is actually the topic here, this smoothing mesh technique, is clearly more time consuming, but gives you more freedom to get a deformed mesh here, which you can use in the computation of your electromagnetic field. And that is that we do a kind of a standing here pseudo-mechanical computation. So we now assume here that in this gray part, we also compute the mechanical field. We fix the mechanical displacements along this dotted line. Along the yellow line, we prescribe the mechanical displacement we have obtained from the mechanical computation of this part here. And so you solve a standard linear mechanical problem with prescribe directly inhomogeneous directly boundary conditions, which are exactly the mechanical displacements along this line here. And doing such a case, you then get here deformations within this gray part. You will deform somehow all the finite elements, but hopefully deform them in such a way that the elements are not too much distorted. And here you have a lot of freedom, especially you can use any mechanical material tensor stiffnesses as you want. It could be even anisotropic, and that is actually what one is using in order that you can apply this smoothing mesh technique as long as possible. Clearly, it's not possible with this technique to compute a contact problem. So when this piece gets in contact with this pole here and this pole of this iron core. And that you can see now here, that are actual computations here of this lift magnet. So this is for different time steps. Looking here, you see already still a very nice mesh here. Here, small distortion. If you look at this, already larger distortion, but still a lot of the other elements are not heavily distorted. So that's quite nice. Even now, where the air gap is already quite small, let's have a zoom here. I would say these distorted filament elements are still okay and give you a good accuracy. Clearly, at some point, you will have to stop with this approach, and then the only possibility without any other techniques would be to do a remeshing of the deformed structure you have here. But please consider, if you do a remeshing, then you also need the interpolation operation of the computed magnetic values you have from the old mesh to the new mesh. Okay, so this is at least a possibility for all the problems we quite often have, where we especially have solid body motion, but also deforming bodies due to electromagnetic forces, excluding to have contact. And that is quite efficient. In the other case where you always do a remeshing, that you don't have these problems here, then you always not only have to do a remeshing, you also have to do the interpolation step. Okay,